All right, so here is the moles of acid that we started with, yes? So after we reacted the base with this, how much A minus is left?
0. Oh, A minus?
A minus.
Yeah.
This amount, yes?
Yes.
Does that make sense? 0.02026. Or we could just say that the concentration of the A minus is what?
You forgot a 0 on that. It's 0.0. No.
We multiplied it, we divided by this. But what we need to do to find the new one is it's going to be 0.02026 moles. If we want the concentration of the A minus, it's not only the 100 milliliters, it's also what?
Plus 46.58.
Is that what it was? That was your equivalent? Yes? Could you say that one more time?
46.58.
So that will now give us the concentration of who? The A minus. 0.02026 divided by 0.14658. Stumpter. Did you get 0.138218? So that's the molarity of the A minus, yes?
Yeah. 1.38 times 10 to the negative 4.
No. You've been getting weird stuff lately.
I did 0.02026 divided by 146.58. Point 0.46. Point. Because that would be a milli. Yeah.
Is this all of the
This is just D.
Yeah, now I got it.
Well, if all of it's
So what is it now? Point what?
Whatever you got it.
0.138218.
Yeah.
So at that point, all we have is A minus, yes?
Yeah.
And we know that that's going to react with H2O. Since this is the conjugate base, it's going to make the acid and OH minus. So at that equivalence point, we have 0, 0 of this, but then this starts happening, yes? How much of this do we lose? Minus X. How much of these two do we gain? And then here we have 0.1608 minus X. I'm sorry, 0.138218. I'm using a crutch to help me do this off of here.
He's got the key. He's got the key up.
I've got I've got a crutch here. What part of the table is what? This is right here.
No, in the other table.
It's not in the other table. It is the number of moles of our acid originally divided by the total volume now.
So all the acid we added.
It's the concentration of A minus. So we added base to it, yes?
Yes.
And that base had a volume, yes?
Mm-hmm.
So the volume is changed, right? Remember in our BCA table, we had to add up and divide by it later. Well, since we experimentally know the number of moles is equivalent with the OH minus and the acid, yes? This is now the number of moles of A minus divided by the new total volume. All right, let me take a look at this real quick. So remember, we have the conjugate what? Base. It's going to react with water to pull the H's off of H2O and make OH. These are our products. This is our reactant. We don't care about water because it's equal to what? 1, because it's a liquid. So we are going to have our X's up here and our A minus down here. Now, in reality, since we know the pH at equivalence, right? It's a big, keep with me here. Since we know the pH at the equivalent, which one of these can we get? We can get the OH minus, right? We would just take and backwards figure out, you know, what the pH is, take the antilog of the negative of that, and then, or we could do what? Take 14 minus it. You got the pH at, can you look on your graph? pH at equivalence point.
0.82.
Is that right, Matthew? So that's the pH. So if we do 14 minus this, Solomon, what is it? 3.18. Did I beat you at another math? On video?
I was yawning.
He said he was yawning if you couldn't hear that on video. So this is the POH. Now what do we do to find that hydroxide ion concentration? 10 to the negative, right? The antilog of that. That will equal the hydroxide ion concentration, which is also equal to what? Right? And then this is what we have minus that, yes? That will give us Kb, yes? So if we know the Kb of the conjugate acid, how do we find the Ka of the acid? You got it. She's got it. I got it right here. 1 times 10 to the negative 14th divided by the Kb will equal the Ka, yes? Is that enough, do you think, for you guys to get together with your lab partner and work through the rest? Are our results going to be amazing for this? Who is going to have the worst one in here? Well, it's probably going to be somebody that didn't fake their data, Matthew. All right.